Here is a magnet and a coil of conducting wire. When the magnet is inserted into the coil, the needle of the microammeter connected to the coil moves. When it leaves the coil, the needle moves again. This shows that the coil generates an electric current, and when the magnet is moved faster, the current is stronger. The magnet produces lines of magnetic force running from the North Pole to the South Pole. This forms a magnetic field. Electricity is generated when the coil cuts across the lines of magnetic force. This is called electromagnetic induction. This multi-layered coil generates more current than the previous one. In addition to this, if we use double magnets to create a stronger magnetic field like this, the coil generates even more current. Now, let's try to generate a continuous current. At the center of this model is a rotary magnet. A coil is wound around the magnet. We rotate the magnet. You can see the needle of the microammeter start to move. When we turn the magnet faster, the needle moves more. As the speed of rotation of the magnet increases, that is, as the coil cuts across more magnetic lines, more current is generated. These experiments show the following principles. The faster the conducting wire cuts the magnetic field, the more current is generated by electromagnetic induction. The more current conducting wire wound around a coil, the greater the induced current. The stronger the magnetic field, the larger the induced current. These 3 points are very important because they are basic to knowing how to control the amount of power the alternator generates. Now, we'll look at the alternator that is actually used in a car. We will explain how the most widely used type of alternator works. That is, one equipped with an IC regulator. The alternator consists of a pulley, frames, a stator, a rotor, an IC regulator, and a rectifier. The last 2 parts will be discussed later. In the alternator, the rotor corresponds to the magnet you saw in the experiments. The rotor consists of a rotor shaft, 2 cores, a rotor coil, 2 slip rings, and so on. When the current flows to the rotor coil through the slip rings, one of the cores becomes the North Pole and the other becomes the South Pole. That is to say, the rotor becomes an electromagnet. The strength of the magnetic field can be changed by varying the amount of electric current supplied to the rotor coil. The next component is the stator. The stator corresponds to the coil in the first experiment. When the rotor rotates inside it, an electric current is generated in the coil. 3 coils are wound around the stator, and they are connected together at one end, which is called the neutral point. This is a circuit diagram of the stator coils. This is called a Y connection, and the point of connection in a Y connection is the neutral point. Now, using an oscilloscope, let's observe the current generated in the coils of the stator. You can see that an alternating current is being generated. This is actually a three-phase alternating current. It is very important to notice that the current generated in the stator is an alternating current, not a direct current. That means that it cannot be used in a car as is. This is because all the electric components in an automobile work on a direct current. Direct current is also needed for charging the battery.